Hey guys, this is CodedSteele and welcome to another circuits lesson. This is lesson 3. Today we're going to discuss Kirchoff's current law and Kirchoff's voltage law, abbreviated KCL and KVL respectively. So first of all, what do these things mean? How do we use them to analyze circuits? Well, first of all, Kirchoff's current law and the voltage law basically state one thing. It states that the sum of the current going through a circuit must equal the total current. And for Kirchoff's voltage law, we replace current with voltage respectively. So the sum of the current going through a circuit must equal the total current going through the circuit. So basically what that means, guys, you can't get more energy out than what you put in. Kind of makes sense, otherwise you're defying a law of physics. So the same thing with voltage. The sum of the voltages existent in a circuit must equal the sum of the total source voltage. So how does this help us analyze a circuit? Well, now that we kind of know what this means, how does it help us analyze a circuit? Well, let's look at this. Let's look at a simple little problem here that we're going to do. We're just going to do, you guys should remember the resistor symbols from our last tutorial where we talked about nodes, loops, branches, voltage sources, and current sources. So hopefully you guys watched the previous tutorial and you know what these components are. Otherwise, you might not understand what's going on. So what we got going on here, let's just say this is a 4 ohm resistor here and a 6 ohm resistor here, and this is a 15 volt source. Well, we can apply Kirchoff's voltage law to sum the voltages going through the circuit and figure out, make sure that we get the correct voltages at a specific point in the circuit. So how do we do this? Well, like I said, we can apply KVL. How do we apply KVL? Well, in order to apply KVL, we have to understand one thing first. That the total current going through a loop is the same going through each element. So this is what I mean. The total, if we have a certain amount of current that's sourced by a supply, that current travels through every element of the loop because the charge only has one place that it can go. So what we see is that elements that are in series with each other have the same current going through them. But say we added another loop over here, now there's 2 loops, so there's going to be 2 different currents because the current is going to split at this node right here. And you're going to get an I2 and an I1. And then they'll recombine down here back into IT again. So I total. So you guys can see this is a very important concept that we have to understand, is that current splits when it goes into different loops, but the current going through a loop, through a continuous loop like this, is the same. So the same current goes through both the 4 and the 6 ohm resistor. So now that we kind of understand that, we can apply KVL here. How do we apply KVL? What we do is we pick an arbitrary point in the circuit and we start analyzing from there. So what we do is we say minus 15 volts. Where does the minus come from? When we're going up this route here, we hit a minus sign. So that's where the minus 15 volts is coming from. And then we add, because voltages are applied like so. So we have an adding of a voltage. What's the voltage here? Well, we don't know the voltage there, but we do know it's this. Using Ohm's law here, V equals IR, we can say that the voltage here must be IT times the 4 ohm resistor. 4 ohms for the resistance, and IT is the current going through the circuit. So then we can say 6, this is another IT times the 6 ohm resistor, applying same Ohm's law. Ohm's law gets applied to every element in the circuit, guys. That's another important concept. Ohm's law can be applied to every element in a circuit. So that's what we're going to use from here on out to analyze every single circuit that we ever deal with. Is going to be Ohm's law. So, and then we say they're equal to 0. Now, why is it equal to 0? Because if it's equal to anything but 0, we're adding energy to the circuit. Remember, guys, this is the source voltage over here. So if we had something over here, then we have a problem, and that means we're gaining energy somewhere, and that's not a good thing. So what we need to do now is move some stuff around. I don't know why I erased that. Is move some stuff around. So we're going to get 15 volts. I'm going to move to this side of the equation, and I'm going to add these two together. So we're going to get IT times 10 ohms equals 15 volts. And then I can just divide both sides by 10, and what I end up getting is 1.5 amps going through the circuit. So we were able to find the total current going through each element in this circuit, and then if we wanted to find the voltage going through each part, we can just take this 1.5 and multiply it by 4, and I think we're going to get like 8 or something like that. No, not 8. What am I saying? 6, and then we're going to get 9. So 9 plus 6 is 15, so we didn't gain any energy. We did a good job. It means we analyzed the circuit correctly. So that's how you can kind of apply KVL. Then we've got KCL, the Kirchoff's current law. So it's relatively close to the same thing, and that we can say this. We have, let's just say we have 3 amps going through a circuit, and we'll just say we have a 1 ohm resistor here to make things easy for us, and a 3 ohm resistor. Actually, we'll even make it a 2 ohm resistor here. So we know this already based on what we said before, how current behaves in a series circuit. We know that the same 3 amps is going through this whole circuit. Since this is a current source, it's applying 3 amps to this loop. So since we know that, we can say by inspection that the voltage in the circuit, which is what we're going to be looking for, the total voltage supplied to this circuit. So that's VT. How do we find that? Well, first of all, we can pretend this is a voltage source and say minus VT plus, how do we find the voltage here? Well, it's simply this current times that resistance, Ohm's law again. So 3 times 1, and I'm just going to label that volts now, plus 2 times 3, and label that volts. And then that's equal to 0. And what we get is VT is equal to 9 volts. So that's kind of how we can apply these laws to find, or KVL and KCL to find the voltage or the current going through a circuit. So we end up with our 9 volts. And then at that point, since we know a current source doesn't exist, if we really wanted to, we could replace this with that voltage source and just say 9 volts here, because that would be how we would build the circuit in real life. We'd hook 9 volts up to a 1 and 2 ohm resistor, and we get our 3 amps going through the circuit. So hopefully that's all making sense to you guys so far, because the next thing we're going to do is we're going to talk about deriving something called voltage division and current division. So we're going to talk about VD and CD, current division. So no, VD is not like some kind of a venereal disease or anything like that. It stands for voltage division. So ha ha ha, you know, kind of funny, whatever. But anyways, we're trying to find out how to derive the formula for voltage division. How do we do that? Well, what we're going to do is we're going to set up some kind of a generic circuit network here, R1 and R2. We're not going to give them any values. We're just going to give them a generic stuff in general. So what do we know about this circuit? First of all, we know there's an IT going through this circuit. So, and we know there's a total voltage applied through this circuit. That doesn't help us. We're trying to figure out how to derive this voltage division expression. Well, what we can do is we can start with a KVL. We can say VT equals IT times R1 plus IT times R2. And that's equal to 0. Well, we're still not getting very far yet, guys, because I'm telling you, this is what we're trying to find. We're trying to find this. V1 equals Vt times R1 over R1 plus R2. This is the formula we're trying to derive. These two formulas are what we're trying to derive here. So we need to get this to look like that somehow. Well, as you can see, we got quite a ways to go yet. But what we can kind of do here is we can say this. We can take this IT and we can say R1 plus, or we can factor it out of the R1 plus R2 combination and move Vt to the other side of the equation. So now we've got something that looks kind of like this. We're getting there, but we're still not quite there yet. So what else can we do here? Well, we know this, that IT, the total current going through the circuit, is the current that's going through resistor R1 or through resistor R2. So we know that the voltage divided by the resistance, so a voltage across resistor R1 divided by the resistance of R1 gives you the total current going through the circuit, since the same current is going through both elements in the circuit. So the opposite, this is also true. VR2 over R2 is also true. There's two different ways to get you IT. So we can substitute this in, and what we're going to find is that we're going to get something that looks kind of like this. We're going to get R1 plus R2 over R2 times VR2 equals VT. And then what we can do is we can move, hopefully you guys can see at this point that we can just move this to the other side by multiplying by the reciprocal of this, and we get VR2 is equal to VT times R2 over R1 plus R2. So, looks like, other than me naming it a different name, it looks like we got this formula. And in the same respect, I could have plugged this in and gotten this one. So, hopefully you guys see that this is how you derive, this is the voltage division expression, and that these two expressions match. Hopefully that makes sense to you guys, how I derived them too. So now, from now on, I'll be able to use this formula for a two resistor network. So from now on, I'll use that instead of going through and using KVL, doing KVL and KCL. This will make it a little easier on us. So now that we derived voltage division, we got to derive the current division formula. But deriving current division means this. Current division means that what, guys? The current is not the same. How do we make it to where the current is not the same through a circuit? Well, first of all, we do another generic little source here, and we're going to do another generic resistor, R1. Now, if you guys remember what I said before, in order for this current to split, elements have to be what's called in parallel with each other. So what we had before was a series circuit where the resistors were hooked up to each other like this and fed back into a source. Well, that is a series combination. This is a parallel combination. And in order for current division to work, you have to have a circuit set up that looks kind of like this. Otherwise, if you had the other one, current is the same, so it won't split at all. So let's work on deriving our current division. Current division is this. So I've got two different currents here, I1 and I2. So I1 is found by doing R2 times the total current divided by R1 plus R2. And I2 is found by doing R1 times IT over R1 plus R2. Hopefully you guys can see the differences between voltage division. All you do is you just swap the resistors. So I1 is R2 and I2 is R1. So you just flop the resistors. Voltage division, we had the same resistor, V1 R1, V2 R2. For this, it's I1 R2, I2 R1. So it's important that you guys make sure you remember that. The easiest way to remember that, the easiest way for me to remember stuff like this is that current takes the path of least resistance. or most of the current will take the path of least resistance. Charge is going to want to go the direction that it's met with the least amount of opposition. If it's met with a ton of opposition, then it's going to take the path that doesn't have as much opposition. So that's how current works and how it flows. Now that we know kind of how it works, how do we derive this expression? Well, first of all, I hope you guys can see that IT is equal to I1 plus I2. I don't know how else to explain this to you guys, but then the fact that you can see that this current splits, and in order for this current to, this splitting current must be equal to the total current in the circuit. So that's where this expression comes from. Well, as you guys can see, we're still not quite where we want to be yet because we don't have an expression that looks kind of like this. So we have a little bit of a ways to go yet. What do we do from here? Well, what we can do at this point is we can say that IT is equal to I1, which is also V total divided by R1 plus V total divided by R2. Why is that? Because voltage, why is it the same voltage here? Because voltage is the same in parallel. Elements that are in parallel with each other have the same voltage across them. So, like I was telling you before, current elements in series have the same current going through them, but elements in parallel with each other have the same voltage across them. So it's kind of the exact opposite of each other how it all works. Voltage divides in series but is the same in parallel. Current divides in parallel but is the same in series. So current and voltage are like inversely proportional to each other in this respect. So now that we kind of have this expression derived here, we can go ahead and we have to create a common denominator for this. Hopefully you guys know how to do stuff like that, and that this should just be nothing more than VT times R1 plus R2 over R1, R2. The only way I can explain that to you guys, like I said, I just multiply this top and bottom by R2 and this top and bottom by R1, and you're going to get an expression that looks kind of like that. We still don't want VT in this circuit, though. So we need to find a way to get rid of that VT, and we will in just a second. But for now, what we're going to do is we're going to move this to the other side of the equation, and we're going to get VT equals the IT R1, R2 over R1 plus R2. Still not quite where we need to be, guys. We're close. We almost got the correct form there. But what we do at this point is, depending on what resistor we divide by, we're going to get whichever one of these formulas. If we divide by resistor R1, we're going to get the current going through I1. So VT divided by R1 is going to be I1, and it's going to be R2 IT times R1, or divided by R1 plus R2. And if I divide by R2, I'm going to get the opposite one. I2 equals IT times R1 over R1 plus R2. So hopefully you guys can kind of see how these formulas hopefully this makes sense to you, how these were derived. And you can see that if you look up there, they match with each other. So that means we did use the formulas correctly. So that's current division and voltage division derived for you guys. And we're just going to end this video off with one example of just one of each, voltage division and current division, just really quick examples. So I'm just going to create a 10 volt source here, and I'm just going to do a 2 ohm resistor and a 1 ohm resistor here really quickly. So we're going to use voltage division to find the voltage here across the 1 ohm resistor. How do we do that? Exactly what I said. We use voltage division. So V of the 1 ohm resistor is equal to the resistance of the 1 ohm resistor times the voltage. So the resistance of the 1 ohm resistor is 1 ohm. The voltage of the source is 10 volts divided by the total resistance, which is 3 ohms. Hopefully you guys can see that V1 ohm is going to be 3.33 volts, a third of the circuit voltage applied. So then that means obviously the 2 ohm resistor has 6.66 approximately across it. So there's our first example of voltage division. Hopefully you can see that this is the VT, and this is the R1, and this is the R1 plus R2. I just added them up really quickly to try to get through the example really fast. So that is our example that we're going to use for voltage division. Hopefully that makes sense to you guys. Now we're going to do our example for current division quickly too. We're going to say 3 amps, and we're just going to do a 4 ohm resistor and a 6 ohm resistor. And we're trying to find the current going through this resistor here. How do we do that? Same thing as I said before. The I of the 6 ohm is equal to 3 amps, which is the total circuit current, times the opposite resistor, which is 4 ohms, divided by the total resistance of the circuit, 4 plus 6, or well, not the total resistance of the circuit, sorry, the combination of the resistors added together, 4 plus 6. And hopefully you guys can see that this is just going to be 4 over 10, which is going to be 2/5, which 2/5 times 3 is 6/5. So I have the 6 ohm is going to be 6/5 of an amp. So approximately 1.2 amps going through it. So that must mean that this one's going to have 1.8 amps going through it. So this will be 1.2 amps, and this will be 1.8 amps. Yep, there you go, 1.8 amps. I think that's right. 4 over 10, 2, 5, yep, 6/5. Yes. So that is a crash course on current division and voltage division. I moved rather quickly through that, but I don't want 30-minute videos, guys. I'm trying to make these pretty short so you guys don't have to tolerate me talking for hours and hours on end. So hopefully this stuff makes sense to you guys. I wanted to cover how you add series resistances and parallel resistance, but we'll talk about that stuff next time because this video is long enough. So please like, comment, subscribe, and I will see you guys for your next lesson in electric circuits.